In this video, we'll be looking at the Unit 4 Review A. This is the final unit. We are making it to the end, y'all. So, according to my Word document, this is page 148, but I'm sure it's might be a little bit different on the paper one you got. All right, so here we're just completing a sentence. In any experiment, the set of all possible outcomes, that is called the sample space. Oh, come on now. So maybe we should even add in here in any probability experiment. That's really what we're talking about here specifically. So when an event can't possibly occur, its probability is 0 or 0%. And when an event is certain to occur, its probability is 1 or 100%. So remember, all probabilities are numbers between 0 and 1, and they can be written as percents, like 0% to 100%, or decimals or fractions. So when we're determining this one, which of the following could represent a probability, we're selecting all the numbers that are between 0 and 1. So all of these are between 0 and 1. Notice all negative numbers are excluded, and any number over 1, if you're wondering like, well, this isn't a number over 1 or whatever, that's 1.1 as a decimal. All right, so if we roll a die one time, find the probability of getting a number greater than 2. Well, we should really say here a standard die. Those of you that are into role-playing games or Magic the Gathering or other kinds of things know that there's more than just a 6-sided die. This book assumes everything is a 6-sided die. So the sample space is this, and if we're looking at a number greater than 2, notice we can't include 2. So these are all the possibilities for numbers greater than 2. So there's 1, 2, 3, 4 of them, and then there's 6 total possibilities. So we could, that's a perfectly acceptable answer. So is 2/3, and so is 0.666, repeating. Notice 2 divided by 3 in our calculator gives us 0.6 forever, which maybe we would round that to 0.67. All right, then if we roll a die one time, find the probability and get a number less than 4 or an even number. Well, okay, so this one is maybe slightly unfair because we didn't talk a whole lot about this, these overlapping, but it's still doable if we just count up all the numbers that are less than 4 and even. So here's all the numbers less than 4. Notice one of these numbers is even, the number of that number 2. We can't count that twice. So we've got 3 possible outcomes, and then for the even part, it's really 2, 4, 6. Again, as I already said, we can't count 2 again, but we can count 4 and 6. So there's 5 out of 6 ways we can roll a number that is less than, less than 4 or an even number. Notice if we convert this to a decimal, it's about 0.83. By the way, I should be also noting we could write these both as percentages. Okay, here's another one. A box contains 5 blue, 8 green, and 3 yellow marbles. Let's quick get that sum. So 5 plus 8 plus 3. I could have done that in my head, but that's whatever. So that's the sample, the size of the sample space, 16. And then if we're going to select a marble at random, what's the probability that it's green? Well, there's 8 green out of the 16, so this would just be 8 out of 16, which is 1/2, or 0.5, or 50%. All of those representations are the same thing. All right, now here comes another one. And in a classroom, the students are 9 boys and 4 girls. Okay, so quick size sample space is 13. If one student is selected at random, what's the probability we've selected a girl? That's 4 out of 13. If we want to get that as a decimal, we do 4 divided by 13, of course, and that's approximately 0.31 or 31%. Again, all 3 of those numbers are accurate representations of that answer. All right, so here we're going to plan to sample members of exercise facilities in your city. Identify which of these types of sampling is used by indicating the correct number in the blank. Okay, well that doesn't make any sense. We're circling. That should be deleted. So we're circling the correct answer. All right, we get a list of all 15 facilities. So this is the population in that city, which you number from 1 to 15 or 0, 1 to 15, whatever. And then you're using random numbers. You choose 3 of the facilities and interview all of the members in each facility. Okay, notice we're grouping. We're grouping these people. So I was mistaken here. This is not the population. The population is all members of exercise facilities, all people that exercise. And we've grouped those members by the facilities they frequent. And then we've randomly selected 3 of the facilities and interviewed all of the people that go to those facilities. That is a cluster sampling because we've grouped by characteristic, and then we're talking to everyone from the randomly selected group. All right, so then we list all of the members. There's a description of the population. All the members of all 15 exercise facility, and randomly choose 400 members. We haven't been told how they're randomly chosen, but this is just a random process. All right, and then we get another list. We alphabetize them and select every 50th. Okay, that's an example of systematic. You obtain a list of all members, and you compile their names into a master list. You get their ages, and then you select 100 members from each age group. That's stratified because we've grouped by characteristic, in this case, age group. And then we're randomly selecting a specified amount from each group. All right. Here is a stem and leaf plot. It's an experiment in botany class. We've got plants in a greenhouse, and we look at their growth in centimeters after 13 days. This is kind of a bad stem and leaf plot because we don't have a key. I'm just going to assume that this means 13 centimeters, right? And I think this is supposed to be over top of here. I think that's a little bit of a formatting mistake. So how many plants grew to 25 centimeters? Exactly 25. There's only one plant. How many plants grew to 36? Oh, there's 2. Right? This would 36, 36. How many plants had their growth measured and recorded? Okay, we just have to count all the numbers here. So let me erase this mess and let's get counting. 1, 2, 3, 4, 5, 6, 7, 8, 12, 17, 19, and 20. There's a total of 20 data values in this data set. And what's the largest? 59 centimeters, and there happen to be 2 plants right here. Okay. So here, the bookstore is recording the type of books these 30 customers purchase. That means we know there are a total of 30 people right here during a weekend sale. And we've got these categorical data values. So R represents the romance, S represents science fiction, N is nonfiction, and C is children's fiction. And so to create this frequency distribution, our textbook called this a categorical frequency distribution because we're just using categories. We just need to count. So how many R's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 romance novels. And then S's, we got 1, 2, 3, 4, 5, 6. And this looks like a W, but it's meant to be an N. 1, 2, 3, 4, 5. That's a 6, good gracious. Okay, and then children's fiction. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do a quick check that we're right. We're going to add up all these values. So I'm going to show this little summation symbol. That's the sum of all these. So 11 plus 6 plus 5 plus 8 gives us 30. Awesome, we've done it. That's the frequency distribution. So now we're supposed to create a stem and leaf plot. Now I'm going to say that this is super annoying how they gave us the data. They should have organized it for us, listed it from smallest to largest. So I'm going to type in all the data values into Excel. And then I'm going to let Excel sort them. And then I'll create the stem and leaf plot. So I would encourage you to do this if you have to make a stem and leaf plot. Well, you do on the unit, on the review B. On the exam, I am not going to have you construct a stem and leaf plot, the final exam. What I will probably do, if I test your knowledge of a stem and leaf plot, is give you some to read and ask you some questions. Like, I guess I could be super annoying and give you a stem and leaf plot and ask what's the mean of the stem and leaf plot. We'll see. Okay, so in Excel, let me make this a little bigger so we can see what's going on. Let's make this a little bigger. And then I'm just going to sort. So I'm in the menu up here, sort from smallest to largest. And then this is where we'll create our stem and leaf plot from. Now, when you look at this, our numbers range from 50 to 99. So I'm just going to do 50, 60, 70, 80, 90 for my stems. So 50, 60, 70, wrong, 80, 90. We don't want the zeros on there, right? Because the stem is just the one whole number, and it's in the tens place. Then from here, I'm gonna list out those numbers in order. Now, if you're doing this in Alex I believe this is the 4-4 homework, you're just supposed to put the numbers right next to each other, no commas or spaces. It's kind of annoying. Doesn't look quite right to me, but it is what it is. We got 160, and then there's a 71, a 71. Okay, fail. There's actually a 70, and then a 71. So try again. 72 71s, a 73, and 2 6s, and a 7, and 2 9s. And then the 80s, a 0, a 3, a 3, a 4, a 7, an 8, and a 9, and then a 90, we got a 0, 2, 5, 5, 9. So all of these should line up vertically so you can get a picture of it. So yeah, there's that. Okay. All right, so here's some data. And we're supposed to find the mean, the median, the mode, the mid-range, and the standard deviation. I'm going to do this in Excel. And then I'm also going to do it in, part of the reason I'm going to do this in Excel is I can copy and paste. I'm just going to Control C, Control V. Oops. Okay. Let me try again. There we go. All right, so to get the mean in Excel, I'm showing this in Excel because when you do your project, Excel is quite useful, I think. So mean, we just do equal, hang on, equal, and then we do in Excel, the arithmetic mean is labeled as the average. Remember, it may not necessarily be the correct measure of average because the median might actually be a better measure. So in Excel, median is median as the function, so I just started typing. Remember, you have to hit the equal sign. And then mode, I don't need to do this because there is no mode in here. NA, notice I chose mode multi just in case there were multiple modes. Now to calculate the mid-range, I have to do the max minus the minimum. So I'll do that. I'll type max. So that will return the maximum value, and then I'm going to add to it the minimum. So that's recording the minimum value, and then we divide all that mess by 2. So I got to put parentheses around that summation there, and then divided by 2, and that returns our mid-range. Do we have everything? Oh, and then the standard deviation. This is the one where Excel shines the most because finding standard deviation, actually finding standard deviation in Desmos isn't too bad. Since this is a sample, we need to use the sample standard deviation, and there it is. So there's all our answers. Now, the data set is in hours, right? So all of these data values are also in hours. This would be, it didn't tell us what to round to. So 46.7 hours, 44.5 hours, there is none, 46.7, and then that standard deviation 12.2. So when it says which would be the best measure of central tendency, we got to look at these, a couple clues of what would be a good measure. How close are these together? They're about 2 hours apart, so it looks like it's a little bit skewed. Let's go ahead, let me sort this data set, and let's decide, do we think there are outliers in here? So smallest to largest, yep, there we go. 29 is pretty low relative to some of the others. So 29 could be an outlier, could be a low number. Although if you look at the mean, it's higher than the median. So, by the way, the median was calculated by adding these two together and dividing by 2. So there might be outliers. I think I'm going to go with the median here. Because 64.3 and 29.1 could be outliers. Now, I'm being real like, I don't know here with these outliers things, because it's kind of a complicated way to prove that things are outliers. And so for this course, we're just asking you to note that when you're looking at what is the best measure of central tendency, which is the same language as what's the best measure of average, you're choosing between the mean and the median. Those are the two to choose, and you're just trying to evaluate, does it look like the data values are close together, or are they far apart? Are there outliers? That's really all you're looking for. If there's outliers, median is your best choice. Remember, the median is resistant to outliers. Okay, here's the grades on a college exam. Find the mean. Ooh. So this is a tough question. Oh, wait, I was supposed to show these in Desmos, how to find these mean, medians, and modes in Desmos. Let's do that, because on the exam, you may be asked to do that on the final exam. And knowing how to do it in Desmos is going to be useful, because you won't have access to Excel. So notice I put brackets, not the squiggly brackets, the square brackets. And you can see that Desmos is telling us, oh, there's 3 elements in this list. So we're listing all of these data values. I'm putting commas in between, which is what you have to do. I think if you put a space, it doesn't understand what's going on. And then the last thing I'm going to do here is I'm going to set this equal to a letter. We're going to call it A. All right. Oh, there's a problem. What's the problem? Is it because it needs a space? Doesn't like the A. It worked last time I did it. Okay, so we have to do it on the left side. And then I'm going to click this keyboard, and under functions and stats, we're going to have all the things we need. So if I want the median, I just do median and I put in the letter that we found. Hey, 44.5, same thing we got. Awesome. If I want the mean, the letter, 46.675. Awesome. If I want the standard deviation, how Desmos delineates between population and sample is they put STDEV-P for population and STDEV for sample. So 12.196, blah, blah, blah. 12.2 is what we had. And then to do the mid-range, does this give us a maximum? Yes. So we're going to do the maximum of A plus the minimum of A, just like we did in cell, Excel, and then parentheses divided by 2, and there is our value. So that would be how you would use Desmos to find these different values on the exam. Let's hope I don't give you a huge data set. Okay, now for this one, this is a grouped frequency distribution. And what we need is the midpoints of these classes. Now remember, midpoints, just remember that what the textbook did was wrong. Hopefully I made sure to point that out. So our midpoints are really the sum of the lower limits. So that's 50 plus 60. Hang on, let me make this bigger. And then that sum divided by 2. So it's the average of consecutive lower limits. That's the language we use in our stats course. So the midpoint of this class limit is 55. And then the next one, let's check that one out. So 60 plus 70 divided by 2, that's 65. Oh, look, there's a distance of 10 units between these midpoints, and that's actually the width, because the difference of these consecutive lower limits is 10. So we know the next one will be 75, and then 85, and 95 for the final one. That should make a lot of sense. That's how we broke apart this data, because 10% is often the difference between like a 2.0 or 3.0 and etc. Like that's where the letter grade breakdown is. All right, so let me put in the frequencies: 1, 3, 14, 18, and 7. So if you recall, what's happened is we have just converted all of the exam scores. Let me see, how many exams were administered here? So, okay, yeah, fix it for me, please. There we go. So all 43 tests, exam scores, we have converted them to these exact values. So we're saying there's 155, one student earned 55, 3 students scored a 65, 14 students a 75, 18 and 85, and 7 scored exactly 95% on their exam. Is that true? Definitely not. Their scores are between 80 and 89. So this is probably going to be a little bit of a bad estimation. But we're going to go with it. It's the best we can do. We can't do it any other way. So what we have to do is figure out, we have to add up all these scores and then divide by how many. Well, if there's 18 85s, we could add 85 together 18 times, or we could just multiply them together like I've done here. So this is the sum of each of these midpoints. And then if I add that all up, I get the top of our mean formula. So this is the sum of all the scores, 3495. To then get the mean, just like we did before, you take that sum and divide by how many test scores there are, and you get the average score. Now, we don't know quite what kind of data set this is. I'm going to assume it's a sample. There's not a whole lot of information on this, so we're going to say this is an 83.5, and I'm using X bar because that's the sample. If we considered this a population, I would have used the letter mu. All right. So Helga scored in the 70th percentile rank on an exam. If 300 students took the exam, how many students scored lower than Helga? Well, that 70th percentile means she is at or above 70% of all students. So we just have to calculate what's 70% of 300. And I guess I could probably do that in my head, but I won't try. 0.7 times 300 is 210 students scored lower. Okay, so then now we're going to say which one has the higher standard deviation, the larger, and why. So the weights of all dogs at a golden retriever rescue shelter or the weights of all dogs for sale in a pet store. So here's the key point. Well, I don't know. This is a tough one. So here we're looking at a specific type of dog is at the rescue shelter. So presumably they're all going to be fairly close weights since they're the same breed. I guess that's the right word. However, it's a rescue shelter, so you could have, significantly malnourished dogs or incredibly obese dogs based on the type of negligence of the owner of the dog or the previous owner. Who knows? However, if we look at weights of dogs for sale in a pet store, we might consider there's a bunch of different breeds. So then their weights could be all over the place. There might be big dogs and small dogs. Although anytime I go to a pet store, it's been years since I have, there tends to be puppies in there. Like I don't know. I don't even know that this is done anymore, right? I don't know. So I think I'm going to say data set 2 because there could be multiple breeds, meaning there'd be a large spread in types of weights. Although, again, I think pet stores typically have puppies, so those all probably weigh about the same. When you get a question like this, hopefully you catch what I'm saying on the final exam. As long as you make a decent argument about why you think one over the other, I would mark you correct. Because if you said data set 1 because rescue shelters are going to have pets in all various levels of health and weights, I would accept that. Okay, so here we got a professor has these 2 sections of math. One happens in the morning, and they had this mean and standard deviation, and the 2 p.m. class had this mean score and standard deviation. What can we conclude about the students' averages in these 2 sections? Okay, so let's write it out so we can compare them a little more directly. So in the morning, the mean is 72%. That's the center score if the data was not spread out. And the sample standard deviation, which we use for S, is equal to 3.2%. And then at the 2 o'clock class, that mean score is 72%. Oh, they're exactly the same mean. So they perform the same way. Oh, but wait a minute. The standard deviation is 18.2%. If we assume these scores were normally distributed, the first standard deviation away from the mean, above and below, gets us into the failing range. So what could we say? This performed much better because their standard deviation is so much lower. Their scores are bunched closely together. What that also means, let's say better as a class, it also means that here the top score is probably in this group. Best performing individual is here. Because when we get, say, 3 standard deviations away from the mean, we're above 100%, which is probably not possible. Again, that's assuming these are normally distributed. They may not be. But this suggests that there's definitely a much higher score because 1 standard deviation away gets us into the 90%. Okay, here we're to assume the data set is normally distributed. We've got a mean of 13 and a standard deviation of 3.5. We're going to draw the curve. So let's start with that. Remember, the mean always goes in the center, and then we add the standard deviation to get above and subtract to get below. So this is going to be 16.5. That's 13 plus 3.5. The next one is going to be 20. Again, that's 16.5 plus 3.5 again. So that was adding 3.5 twice to this 13. And then the last upper bound is 23.5. So this is plus 1, plus 2, plus 3 standard deviations above. And then below, we're going to subtract. So we got a 9.5, a 6, and a 2.5. We should then put in our percentages. Now, I can't remember if I pointed out in the videos or not. These percentages are approximations, and your author uses a different set of approximations than what the authors of our textbooks for our stat class uses. That's okay. It's not a big deal. You just need to know that there is some slight variation in what people use for these. So our author uses 34.1% for this area, and then 13.6 here, 2.2 here, and 0.1. So that's what we're going to stick for our, is what Alex uses, what I'm going to use for answers on the final exam. I think what our stats class, our 133 class uses is 34%, and then like 13 point something. It divvies up the percentages just a little bit different. And no one is incorrect, let's say that. Okay, so there's our normal curve. Now let's read what these are. Oh, it doesn't, there's no context. We have no idea. So it says, if the data set contains 50 data values, how many values fall within the 9.5 to 16.5 range? Okay, that's here. Notice 34 plus 34, or 34.1 plus 34.1 gives us the area in between the the minus 1 standard deviation, the plus 1 standard deviation. So if there's 50 data values represented by this curve, that just means we're going to do 50 times the 0.682%, and that's how many data values would fall within that range. And that is 34.1. Now we have no idea what, well, actually we do know what this would be. It would be 34 data values, since we're talking about an exact data value. You can't have a partial of a data value. Okay, a couple more of these. So here again, we've got a normal distribution. Notice our mean is 126 and our standard deviation is 20. Ooh, I like that. What happened there? So this is 146, 166, 186. I'm just adding 20 each time. Now I'm subtracting 20, 106, 86, and 66. That's nice for addition and subtraction. We're supposed to draw this. Boy, I kind of don't want to, but I'm going to. These percentages don't change. If we know it's approximately normal, this is always what we're going to write for this class. If you take 133, we write a slightly different number for these percentages. You also get reference sheets in 133. It's a great class. I encourage you to take it if you're interested in stats. Great careers out there. Same question. We have 350 data values. How many are between 86 and 166? So this is 2 deviations apart. So we're going to take these 350 data values and multiply by what percent this represents. Well, it's I guess I'm going to have to use a calculator here. It's the 68.2 that we already had from before plus 2 13.6s. Oops. So that's 95.4% of all data values fall in there based on the approximations we're using. So we just need 350 times 0.954. Remember when we learned how to find a percent? So I think, well, this isn't approximate, this is exactly. I think we would round this to 334 data values. I think we would guess that. Okay, all right, so now we're to assume that males have a mean height of 69.2 inches with a standard deviation of 2.9. Just to connect with the language, this is when it says that males, it's implied all males. So these are population values. Same thing here, mu 63.7, sigma for the standard deviation. So based on z-scores, would a 5'4" male or a 4'10" female be taller compared to the rest of their gender? All right. First, note that our values here are all in inches. So when we calculate the z-score for the male, we're going to need his height, which is a data value, we'll call that x, in inches. Well, we know there are 12 inches for each foot, so we would do 5 times 12 plus the 4 inches. This male is 64 inches tall. So the z-score of the male, recall it's the data value minus the mean divided by the standard deviation. So 64 minus 69.1 divided by, ooh, look at what happened in Desmos. I need parentheses, divided by 2.9. We get approximately, come on now. There we go. Approximately negative 1.76. Remember, these z-scores are unitless. And it's just what this literally means is this male's height is 1.76 standard deviations below the mean. So he's a little bit short compared to other males. However, being being below 2 standard deviations is what we consider unusual. So he's not unusually short, just shorter relative to all males. All right, so for the female, I'll put these subscripts on here so we know what is what. We're going to do 4 times 12 plus 10. So that's 48 is this, plus 10 is 58. And her z-score, 58. Now we got to make sure we use the information for the females. That's 63.7 for the mean and 2.7 for the standard deviation. We'll just smash that in here to get our answer. So 58 minus 63.7. Make sure you got those parentheses, divided by 2.7. Ooh, she's negative 2.11. So her height, she's unusually short relative to females. So who's taller relative to their gender? The male is taller, because his z-score is larger than hers. If you were asked which gender has more spread out heights, it's the males, because their standard deviation is slightly larger. There's more variation in the male heights than the female heights. Okay, one more, same thing. Here we got a student that scored this on the SAT test, and SAT population mean is 1026, population standard deviation is 210, and then scored this on an IQ test with, again, population mean and that. So determine which test she did better on. Okay, so same thing. We'll just do a z-score here. We don't have to convert any units, thankfully. So here's the SAT z-score. It's the data value minus the mean of all people who take the exam divided by the standard deviation of all people who take the exam. And I believe how these population means are considered, they do it by year, but I could be wrong. Maybe it's by version of the test. Okay, her SAT score is just slightly above the average SAT score. If I were to round correctly, I'd put 0.96. So under 1 standard deviation above. All right, how about her IQ test, which I've heard there's a lot of bias in these IQ tests, racial bias and gender bias. All right, so it's 110 minus 100 divided by 15. So let's do that. Oh, according to her IQ test, she's not as bright as the SAT. Although remember that these are used for very different things. This is a college entrance exam that colleges are actually moving away from, and this IQ test was like it's like your intelligence quotient is what's that called, and it's like supposed to measure your smartness. So the SAT is more a measurement of, did you learn all the things from high school that you need to be successful with like a liberal arts college degree. And the reason I say liberal arts is because you're taking those general education classes. So the SAT is looking at what are your mathematical skills, your computational skills. How about your English, your vocabulary level, and your ability to read texts and answer questions, that kind of stuff. So which test did she do better on? SAT, because 0.95 is greater than 0.67, those z-scores. All right, one last question, it looks like, right? Yeah, last question. Sorry, this is going long. So here we got the mean sale price for existing homes in the United States. Here's a typo, oh my goodness, is 213,000. All right, so that's our middle number. Now I'm going to write these numbers in here, not in terms of thousands, but in terms of, I'm going to take off the zeros, and we're just going to say they're in thousands. So I'm going to make that 213, and then I'm going to add 44 to that. You can see why. It's easier to write. So this is 301, and this last one is 345. Okay, I'm not confident with that one. Yeah, I should have been. And then subtracting, I'm going to go ahead and be lazy. And, well, it's not lazy. I just don't want to make a mistake, right? So here's 169, and then I'm going to subtract another 44 from that to get the next one. That'd be 125, and then subtract one more, and that's the 3 standard deviations below the mean. Now remember, these are all in thousands. Man, I don't want to do this, but we're going to again because it's good for you. So I know these, right? Although I usually use the stats one instead of the one we're using here. This one's 2.2. I suppose I should also put the percentages on here. This is 13.6%, and this is 34.1% based on our textbook. Same on the other side. All right, so we're going to find the percentage of existing homes that were sold between these two numbers. You'll notice that any questions we give you in this class related to amount of homes, related to the number of data values up here, we are always asking percentages on exact standard deviations. And you might be wondering, well, what if we picked a number somewhere in here, like 130? What percent sold below 130, 130,000? If you're interested in that, take our 133 class. We teach you how to do that. All right, so we're adding up all of these percentages. So we have two 13.6s. That's this one and this one. And then we have two 34.1s. And I happen to remember that we used this number in one of our calculations before, so it's 95.4%. Don't round these percentages. These values up here are approximations already, so when we're adding them together, leave it with what you got. All right, how about sold for more than? So here we're above this and we're going on forever, so we need 13.6% plus 2.2% plus 0.1%. Those three things, let's see, this would be 15.8, so 15.9%. You might be tempted to write that as 16%. Don't do it. This is an approximated value already. You don't want to double approximate things. All right, that's it for the unit review A. So your job is to do the unit review B. I don't know if I've told you this before. This is exams I gave back when we met in person, what seems like many, many years ago, which was only about a year and a half, well, I guess a year ago. So this was an actual exam that was given. I'm using these as practice questions now for you all. Work through it carefully. There's a few ones that are a little tricky. When I write the final exam, I'm going to be modeling the questions on the final exam based off of these questions, just like what I did with the midterm. Don't forget, if you have questions, please email me, come to office hours, or set up a time that we can meet. I want to help you get through this. We're right at the end, y'all. Hang in there, kick it into high gear, and let's finish this class out strong.